All right, so I guess we'll get started. So I'm Mike Lawrence, and I thought I would give this talk. It's in association with, but not exactly part of the Attention Symposium. It's mixed effects modeling for cognitive science, a tutorial. So the reason why I'm doing this is because I've very recently learned about mixed effects modeling and have become completely enamored with it and feel that it's the tool of the future. ANOVA is dead. We can all stop using it. It's got more assumptions and it's less statistically powerful, also less reliable than mixed effects modeling. And there's a whole bunch of really cool things that you can do with mixed effects modeling that you can't really do with ANOVA, or if you're doing it with ANOVA, you have to do a whole bunch of things by hand, and it's inefficient both in terms of your time, but also statistically. So I thought I'd start off. So the tutorial structure. I'm going to start off talking about a simple Gaussian model of mixed effects, and then a slightly less simple Gaussian model. Then I'll talk about binomial mixed effects models. And then I'll talk about generalized additive mixed effects models. And then at the end, I'll have a bit of a discussion on actually using mixed effects models for scientific inference. So most of the talk will just be about the idea of creating these models. The last little bit is how do we use these models for answering inferential questions. So that will include sort of models, parameter estimation, and quantifying predictive success. So a simple Gaussian model. So let's consider an experiment where we collect simple RT, so how fast somebody responds by pressing a space bar on a keyboard after they've seen some visual stimulus, for example, measured across multiple trials within each of multiple subjects. So this idea where we have multiple trials within each of multiple subjects means that the data is hierarchical. That is, there's trials within subjects. And a naive, non-mixed effects model of this scenario would simply say, OK, I'm going to say that the reaction time value on a given trial for a given subject is determined by this equation. Grand mean, so the mean across all subjects and all trials, plus error. And in this naive model, typically in a lot of statistical contexts, we model error as this normal distribution. So it's the normal or Gaussian distribution with a mean of 0, so the error doesn't bias the equation, but it's got some variability. Now, I'll often talk about variability, variance, and standard deviation here. I use them pretty much interchangeably, although variance is, of course, the square of the standard deviation. So this sigma e represents the standard deviation of error in this simple naive model. But we all know that this is a silly model because we know that people differ from one another in terms of how fast they can react to things. So to account for variability in participants in mean RT, we want to incorporate a new term representing each subject's deviation from the grand mean. So we have a less naive model. The reaction time value on a given trial for a given subject is determined by this equation. So the grand mean plus the subject's deviation from the grand mean plus error. So here we're taking into account that variability that we all know exists between people in terms of their overall mean response. And again, error is modeled as a Gaussian distribution with variance of, with sigma e standard deviation. And now, in the context of mixed effects modeling, we're going to say the subject deviations are actually captured by yet another Gaussian distribution, again, with a mean of 0, but now a variance or a standard deviation of sigma s. This differs from ANOVA in the sense that ANOVA will typically not model the subject deviations from the grand mean. It just assumes that, or it will explicitly compute the subject means and use those and just put those into the equation and subtract those out from each subject. Whereas this actually models the subject's deviation from the grand mean according to this Gaussian distribution. That has some benefits that I'll talk about in a moment, but just to reiterate this very simple Gaussian mixed effects model, I want to walk through it as an algorithm. So if we wanted to generate data from this model, what we would do, we'd set the grand mean to some value, we'll call it GM, and then for each subject, call them I, determine subject I's deviation from the grand mean by sampling a value from the Gaussian distribution with the mean of 0 and the standard deviation of S, and call that value S dev I. And then for each trial within that subject, determine the error for this trial by sampling from sampling a value from, again, another Gaussian distribution, mean of 0, a standard deviation of sigma E. And that gives you the error for this subject on this trial, so Eij. And then finally, the reaction time for that subject on that trial, RTij, is the grand mean plus that subject's deviation from the grand mean plus that trial's error. So to again summarize this model, there's 3 parameters in this model: a constant and 2 variances. The constant is the grand mean, and the 2 variances, so the constant's the grand mean, we've got an error variance, well, that's a standard deviation, and the variance of subjects' deviations from the grand mean. So we've got sigma E, sigma S, those are variabilities, and we've got the grand mean as a constant. So fitting this model to a set of data involves finding the value, estimating the value of these 3 parameters. So we need to estimate the value of the grand mean, we need to estimate the error variance, and we need to estimate the variance of subjects' deviations from the grand mean. So I guess just to back up and contrast that with ANOVA. In ANOVA, typically this is just, ANOVA attempts to simply subtract this out, whereas we are explicitly attempting to, whereas in the context of mixed effects models, we're trying to explicitly estimate sigma S. So let's look at some slightly more interesting data. Simple RT again, but let's say we're measuring it in multiple trials within each of multiple subjects, same as last time, but then also within each of multiple conditions. So we've got 2 conditions manipulated within subjects, but within each condition we've got multiple observations. So again, it's hierarchical because you have trials within subjects. In this scenario, there's multiple mixed effects models that are available, or that are possible, and I'll present them now in order of increasing complexity. So the first model of this would be the constant, I would call it the constant condition effect model. So in this model, the RT value on a given trial for a given subject in a given condition is determined by an equation like this, where it seems very similar to the ones we've seen before. We've got the grand mean, subject's deviation from the grand mean, some condition effect, so depending on what condition they're in, that's going to be positive or negative, and error, of course. And the parameters of this model, we've got 2 constants. We've got the grand mean and this condition effect. And we've got 2 variances, the error variance and the subject's deviation from the grand mean variance. That's a very simple model. It assumes that this condition effect is constant across participants, that the only error that exists in the data is at the level of trial-by-trial error, that there's no variability in the subjects with regards to the manifestation of this condition effect. We know that in the same way that humans differ in their mean reaction time, we know that they're likely also different in their manifestation of different effects in response to our experimental manipulations. So a slightly more complicated model is a by-subject varying condition effect. So in this scenario, the RT value for a given trial and a given subject and a given condition is determined by this equation. We've got grand mean, deviation of subjects from the grand mean, condition effect. Now deviation of subjects, condition effect from the overall condition effect, and then error. So now we've got two constants, same as before, grand mean and condition effect. Now we have three variances because we've got error variance, subjects deviation from the grand mean, but now also we're capturing the idea that subjects are going to vary in their manifestation of effect by modeling it explicitly as, again, a Gaussian distribution, mean of 0, but some estimable variance. Now, as illustrated on this slide here, we have an error variance, variance associated with subjects with regards to the grand mean, and another variance associated with subjects with regard to condition effect. So we've got these two variances associated with subject. That means that we can, in theory, compute a score for these two properties of the subjects. So we can have a score of the subject's deviation from the grand mean. That's just that subject's mean RT. We can also have a score representing their condition effect. And in theory, those two scores could correlate or not. So a slightly more complicated scenario. So with two subjects, two variances associated with the subjects, we must specify the covariance of these variances. Another way of putting that is that the correlation between subjects' deviations from the grand mean and subjects' deviations from the overall condition effect. And yet another way of putting it, we need to specify the correlation between the subject's means and the subject's condition effects. So we're getting into an area where typically in ANOVA, you're just ignoring these things. ANOVA actually assumes that these correlations are 0. Here, you're actually able to explicitly evaluate these properties of the data, whether there's correlations between these two things, and it's very fruitful for those interested in individual differences and using correlations between measures to make inferences with regards to cognitive structures. So, to reiterate the possible mixed effects models in this scenario, we had the simple no by subjects condition effect variance. So you assume that all subjects manifest the same condition effect with no error, with no variability amongst them. And that has 4 parameters, 2 constants, and 2 variances. You have the second mixed effects model where you have by subject varying condition effect. But we can say that let's just fix the correlation between the, fix the covariance of the subject's mean RT and the subject's condition effect at 0. So that would be sort of the next most complicated model. You have the variability amongst subjects, but it has no correlation. There's no correlation between the subject's mean RT and the subject's condition effect. And then the next more complicated model, so that has 2 constants and 3 variabilities, because we're fixing that 4th variability at 0. And then finally, the most complicated model is where you have by-subject condition effect variance, and you explicitly estimate the covariance between the subject's deviation from the grand mean and the subject's deviation from the overall condition effect. So that yields 2 constants, 4 variances. So we can get pretty complicated models as, I guess, the number of parameters you have to estimate out of your data increase quite dramatically, but you have, this reflects the flexibility you have in mixed effects modeling in answering a variety of questions. And screen appears to be going yellow. All right. So to briefly consider yet a more complicated scenario, 2 predictor variables. So let's consider a scenario of reaction time measured across multiple trials within each of multiple subjects in each of 2 conditions crossed with, say, 2 sets of instructions. So we've got a 2x2 factorial design. Oh, I was touching back. So the most complicated model, so I'm going to ignore the incremental models that one can build. The general idea of this most complicated model, if you want to build simpler models, you can just imagine fixing some of those sigmas to 0. So the most complicated model is where you have a grand mean, you have a condition effect, you also may have an instruction effect, and you can have the condition effect by instruction effect interaction. So you could imagine some simpler models where you say, oh, okay, I'm going to assume that this is 0 or this is 0, and that could be simpler models. But you additionally have this idea of error variance, but you also have many other variances. So this is a picture of the covariance table. Along the diagonal would be simply the diagonal reflects the fact that you actually need to have, or the most complicated model would explicitly estimate the subject's deviation from the grand mean. This is the subject's condition effect deviation from the overall condition effect deviation. The subject's instruction effect deviation from the overall instruction effect. And this is the subject's interaction deviation from the overall interaction. So with all those variances, you can also investigate the covariances amongst them. So there's a whole variety of covariances that, again, are individual differences measures that might be inferentially interesting for you. But the point here is that, well, partially that's as you add predictor variables, you dramatically add the number of variances that you're estimating. But that is a good thing because these are things that might be interesting in your data. So benefits of mixed effects models so far. There's no assumption of sphericity, which is a big one in psychology because we do a lot of within subjects manipulations, and the assumption of sphericity in ANOVA is very often violated. The reason why there's no assumption of sphericity is because sphericity deals with that covariance matrix, and in mixed effects modeling, you're explicitly estimating the covariance matrix. So there's no assumption about the format of that covariance matrix. Another benefit is that it permits the models to account for the variance at the level of the raw data. If you notice, as I said at the beginning, when you have a mixed effects model, if you have hierarchical data, typically what happens is before you do your ANOVA, even though there's multiple trials within each of multiple participants, what you do is you collapse all the participants' information to a single score and then submit that data to the ANOVA. That ends up throwing out a whole lot of information about, for example, the reliability of your measurement. By mixed effects models are happiest when you give it the raw data, so that actually ends up yielding more accurate and more statistically powerful inference. So yes, so you have more power to evaluate effects. You certainly have more power to evaluate correlations, partially because when you're correlating to individual differences variables, the mixed effects model is able to see the raw data, which reflects possible shared variance amongst the things that you're trying to measure. And it's by taking into account that shared variance, it's able to up the power to detect correlations. But furthermore, it's actually more accurate in evaluating correlations. That is, that shared error variance can dramatically affect, when there's shared error variance amongst measures, that can dramatically affect the, the gross correlation that one might compute if you just ignored the shared error variance, such that I've seen cases where you have a significant correlation between two variables by computing the typical approach by collapsing things to a mean. But when you do it the mixed effects model way, it actually, again, supports a strong relationship between these two variables, but in the opposite direction than the traditional approach suggests. And it's being demonstrated that taking into account the shared variance is the more accurate approach. So there are some additional benefits of using mixed effects models than the ones we've covered so far. You can specify multiple random effects. Now, I haven't talked about what a random effect is in the first place. A random effect, my definition of random effect, is that it's a variable over which non-error variance manifests. So non-error variance would be, for example, subjects deviate from one another in their, systematically deviate from one another in their mean RT. But you're uninterested in the specific effect of a specific level. So a specific level, for example, would be a participant. I don't care that this participant's, I have no inferential questions about this participant's mean RT. I just know that there's variability amongst the participants that I want my model to account for and therefore have more statistical power. But I generally don't want to try to make inferences about this person's specific mean RT. So far we've been talking about participants as random effects, this idea that you're letting the participants' mean differ from the grand mean, and effects differ from the overall effects. But you can specify multiple random effects. So for example, in a lot of psycholinguistic literature, they've been for decades wringing their hands over the fact that even once you control for a whole lot of features of words within two word groups, you still find that there's big variability amongst the words if you were to, for example, have 5 words in this word group, 5 words in this other word group, but you measure each word in each person, say 10 times, you still get this big variability, systematic variability within the word groups amongst these words. And people have done a whole bunch of tricks, like you do 2 ANOVAs, one where subject is the sort of unit of repeated measurement, and another ANOVA where word is the unit of repeated measurement, and then we try to combine the F-scores somehow. That's just being solved by mixed effects modeling, because you could just tell your model that these are 2 random effects, and it automatically takes into account all that variability that you were looking to take into account in the first place. So you can add a item as a random effect. So yeah, it permits more powerful inference by accounting for even more variance in the data. So yet more benefits of mixed effects models. Binomial data. There was an issue of the Journal of Memory and Learning. Yes, Journal of Memory and Learning. 2008, where there had a number of articles on the that lauded the mixed effects modeling approach. 2 of them specifically, though, were talking about mixed effects modeling in the context of binomial data. Binomial data is when the observation you make is either this or that. So, for example, the person got an answer either correct or incorrect. The rat either found the cheese or didn't find the cheese. So when your data take one of 2 states, it's binomial. And both of these authors ran slightly different, under slightly different approaches, came to the conclusion that proportions are evil. That is a typical approach when people have hierarchical data, where you have a subject, multiple trials within a subject, is to, before you do your analysis and you're dealing with binomial data, you've got multiple 1s and 0s for a subject, you collapse those 1s and 0s to a proportion. So maybe if it's 9 1s and 1 0, you collapse that to a number of 0.9. Turns out that when you use proportions, it fails to account the fundamental binomial nature of the data. And the end result is that when you apply ANOVA to proportions, when the proportions derived from hierarchical data, which is what we typically collect, you have, depending on the scenario, you can have an increased type 1 error rate. I always get these confused. You have increased error rates, basically. You will, there are scenarios where you will find effects that actually aren't there. There are scenarios where you will fail to find effects when the effect actually is there. It turns out that mixed effects models has much lower error rates in this scenario. This is because they actually don't ask you to collapse the data to a single value. They actually take the raw data in, and you can explicitly specify that this is binomial data. And so to do this, the idea is that instead of this sigma e, which is what we've had in all our models so far to represent the idea that there's variability, there's this fundamental, at the level of the trial, variability in response, they replace sigma e with a random binomial sampling procedure. So to demonstrate this in the context of an algorithm, for comparison to the Gaussian algorithm we had earlier, the binomial model would start off and set the grand mean to some value on a continuous scale of bias. So that scale goes from negative infinity, positive infinity, 0 reflecting no bias. So we'll call that value as the GM. And then for subject I, we determine that subject's i's deviation from the grand mean by sampling a value, which is a Gaussian distribution, mean of 0, and a standard deviation of sigma s. And then for every trial, we sample from a binomial distribution with the probability of there being a 1 or a 0. So probability of 1 as the what's inside here, which is the grand mean plus the subject deviation from the grand mean. And then this inverse logit implies that the this continuous scale of bias is the logit scale, log odds. The general idea here is that we're converting log odds into probabilities. So we're saying the probability of 1 is specified by this transformation from the bias scale to a probability scale. And then once we've got that probability, we then sample from the binomial distribution with that given probability. So usually the inverse logits we'll take a negative infinity to positive infinity scale and scale it to 0 and 1, and then you can sample your data, whether it be 0 or 1, given the probability that you determine on that trial for that subject. So actually, this value then stays constant across trials for a given subject. The randomness comes from the fact that you're sampling from the binomial distribution. So there are some exciting features of binomial mixed effects modeling. Well, in addition to what I expressed before, which is this is the only way to properly analyze data where you have binomial data, there's some exciting extensions of this idea of using binomial mixed effects modeling. One is that it permits one-step application of signal detection theory. So signal detection theory, well-used tool in cognitive science. The general idea is that you've got an observer, and that observer is trying to make a decision with regards to the class of two types of stimuli. Or more specifically, what class a given stimulus will fall in given two types of stimuli. So we may have stimuli from the red curve, and they may generate a signalness percept that is along this that is roughly normally distributed along this dimension of signalness. And this other category, the green category, which may have this slightly higher probability distribution along the signalness continuum. And what we're most interested in typically in the context of signal detection theory is determining the subject's transformation of whatever signals we give them into this signalness scale and how far, therefore, the two distributions are separated from one another. So participants that can really easily distinguish two stimuli from one another should have a large separation between the two distributions. Participants who can't actually, or scenarios where the participant can't distinguish the signals between one another very well should yield a small difference in the location of those two distributions. So that's the thing we're typically most interested in. Usually that indexes information processing efficiency. But when you're doing the type of scenario where people are presented with a stimulus and they have to label it as either red or green, there's another component of performance that can affect the data that comes out other than just the separation of the two stimuli, which is where they're going to put their criterion for saying that something is red or green. And participants can use different heuristics for trading off different types of errors that they could be making in this scenario. They could move their criterion really high so that they are really reluctant to call things green. That would allow them to accurately call most red things red, but it would mean that they'd be missing a lot of the green things that are missing a lot of the green things. Alternatively, they could put their criterion the other way and favor green more than red. So the idea here is that signal detection theory allows you to dissociate the effects of response bias versus effects on discriminability. A lot of the time, we're most interested in effects on discriminability because it usually indexes information processing efficiency, and we want to just account for bias and in our models. So the typical approach to applying signal detection theory to hierarchically collected binomial data is within each person, within each condition of interest, you use some analytic formulas to estimate the bias parameter and estimate the discriminated parameter. And that gives you two numbers for that person in condition. And then you do two ANOVAs, one ANOVA on the bias, if you're actually interested in bias, and then another ANOVA on discriminability. That not only is just tedious, because you have to go in and do it somewhat by hand, and there are different issues with maybe you have only a small amount of data in one condition and more data in another condition. Your analytic estimators might have differential bias themselves in estimating these parameters. But it also fundamentally assumes that once you have good estimates of these features, that those estimates manifest the Gaussian the Gaussian variability that you have to assume in the ANOVA. In contrast, when you do mixed effects models, you just submit the raw data. And specifically, you make an equation where your analysis is saying, okay, I want to look at what subjects say, so you're predicting response as a function of all your predictor variables, but you also add what reality is. So so if they saw green, so you'd have trial by trial data. Say they said red. On the one of the columns in your data is what the actual stimulus was. Maybe it was red. So you have red on this side, red on the predictor side, and then you'd have green, and maybe the thing was actually still red. So you'd be including reality as a predictor variable of response. And the idea here is that effects that don't include reality as, so for example, if you had a main effective condition on response, that means that they had a higher probability of saying one response over the other in one condition versus the other. And that simply is a reflection of response bias. But if you additionally had a effects that interacted, so if the condition effect interacted with reality, then that would say that I guess that would reflect an effect on discriminability. Insofar as the sort of main effect of reality on response indicates their overall discriminability, if you find that condition interacts with that, that specifies that condition actually affects discriminability. So you don't have to do all this manual calculation and separate analyses for the separate parameters of the signal detection model. You can actually analyze them all within a single mixed effects modeling framework, which is, I found, nice and elegant. Some more exciting features of mixed effects models. So it turns out that a lot of our research data uses binomial functions and, obtains binomial data, but then tries to fit psychometric functions through the data. So one example is the analysis of temporal order judgments. So a scenario here would be you're presented with a square and a diamond on each trial, and sometimes the square comes first, sometimes the diamond comes first. And you simply ask the participants, which one came first, square or diamond? So binomial data, they say one thing or the other. And if you imagine that, there's a number over here. But if you imagine if you presented them at the same time, that is reflected on the x-axis here as 0 separation. If you put the square as leading the diamond by a whole second, most people are going to respond most of the time as saying, okay, the square came first. If you put the diamond a whole second before the square, that's going to come over here, then most people are going to say, okay, the diamond came first. But there's going to be some sort of monotonic function relating, going to the point where they're going to be perfectly uncertain at around 0, and it goes like that. So a typical function that you observe is something like this, where they have low probability of saying square when the diamond actually came first by quite a bit, high probability of saying square when the square came first by quite a bit, and then in the middle you get these middling probabilities. And the things that we are usually interested in a function like this is its location and its sort of tightness, how it's shaped, or scale, I guess is the official name of the parameter. So a sharper bend in the curve, a tighter scale, reflects better discriminability of reality, whereas the shift simply reflects a bias for response. So again, we're talking about bias and discriminability. It's very similar to the context of signal inspection theory. Typically, again, when people have used the psychometric models, they would go in within each condition of their experiment. They'd estimate out the scale and the location of the bias and discriminability indices in each condition by hand, and then try to submit those things as separate analyses. But in mixed effects modeling world, you can explicitly model such binomial responses as forming the psychometric function parameterized by bias and sensitivity. So it's really nice and elegant. It takes the raw data and does all the work for you while properly treating the binomial data as binomial. And so, yeah, it allows you to evaluate the effects of manipulations on bias and sensitivity independently. And this applies not only just for this single sigmoid location scale function, as I've demonstrated in temporal order judgments, but all sorts of other psychometric functions that one could imagine. So you can have SAT curves, which generally have 3 or 4 parameters. You can have any parameterized nonlinear function and achieve this in the context of mixed effects modeling and have much more elegant analysis. So one thing that really got me excited last summer was my discovery of, one thing that has long vexed me is the problem of continuous data. So with continuous data, so maybe I'm looking at reaction time as a function of age. And I've collected age across a variety of ages, from university undergrad all the way up to people in retirement age. And now I'm interested, is there effect on age on reaction time? Well, I've got 2 options. I can treat as linear. I can treat the effect of age as linear, in which case I would have excellent power to detect linear effects. If the effect of age truly is linear, I would have good power to detect that. However, I'd have really bad power to detect nonlinear effects. Say there's sort of an initial bump in age and then a sort of asymptotes, effect of age on reaction time. So I'd have poor power to detect nonlinear effects. So another way of doing this is to treat age as categorical in some way. So either I do some sort of split half, which is very common, or maybe I create bins for age and I do that. But I fundamentally treat it as categorical. I ignore the continuous nature of the data. This will have, if the data is actually nonlinear, this will have mediocre power to detect nonlinear effects, so a little bit more better power to detect nonlinear effects than if we just treated things as linear. But it will also have mediocre power to detect linear effects. So you've got this annoying dilemma that you have to make this a priori decision with regards to the likely linearity of your data. And it really vexed me for a long while how to deal with this. I, for a while, started using polynomial regression, but frankly, polynomial regression tends to produce fits that tends to produce curves that just a really unnatural looking, and I got a lot of really weird results from using polynomial regression. Turns out that there's a really elegant solution to this issue, and it's achieved through a procedure called generalized additive modeling. And generalized additive modeling can be applied in the context of mixed effects modeling. So the idea of generalized additive modeling is that it's able to flexibly model both linear and nonlinear effects. And specifically, it balances the functional complexity of whatever function it's trying to fit through the data by optimizing prediction of future data, which is fundamentally what we're trying to do in science in terms of our inference. We're trying to make sure that our models can predict new data. They don't just very well fit current data. So this is just simply saying that generalized additive mixed effects models, otherwise known as GAM with just two M's, simply extends GAM to hierarchical designs. And to just give you a quick sense of the principle of GAM, so I've got data like this. I've got some variable x, another variable y, and I want to say is there a relationship between those two. The eyeball can kind of see a nice linear function going through these. But, I don't know, maybe there's sort of a slight curve, almost like a power function or something going through here. How do I choose between these various forms of functions? Well, I know that the most one way of doing that is to simply try to see which one fits the data best. So one metric of fit is the least squares model, the idea that you fit the function through the data and then you evaluate how far each point is away from the function. But if I use that simple, naive least squares approach to finding a function who fits through the data, I actually can find a function that perfectly fits the data by just connecting all the points. But nobody's going to believe that that function actually describes reality. The reason is because you assume that there's actually some error in this data. And connecting all the points means that we're not only predicting the true trend in the data, but we're also predicting the error. And presumably error is going to differ in the future, then the specific values of those errors that I observed are going to differ in the future if I obtain new data. So we don't want to simply fit a function using all the data, and because in that circumstance, you're going to be, the evaluation of the function will include its ability to fit to error. And of course, that will prioritize those things that are more complicated. For example, the extreme scenario of just connecting the dots. So the way generalized additive modeling approaches things is that it attempts to find a function whose it uses a variety of different types of squiggly functions. But the general idea is that it will fit a function through the data, and then it will evaluate the degree of fit by doesn't actually fit the function through all the data. It forgets one point, fits the function through the data, and then brings that point back to evaluate the degree to which that function is able to fit the data. So, and then it repeats it for all the different data points. So it sort of pre-specifies a complexity level of the data, and at that complexity level, it fits as many functions as there are data points, each time removing a data point, fitting the function, and then evaluating the fit of the function with regards to its ability to predict that data point. And then it will go through a variety of degrees of complexity and find the degree of complexity that optimizes the function's ability to predict new data. So this is a standard it's a gold standard procedure for evaluating models' ability to predict new data whilst controlling for the fact that in the naive approach to fitting functions, more complicated models will tend to fit data better because they have more ability to fit the noise. So this procedure is actually called cross-validation. Again, it's a very gold standard approach to fitting, or I guess, model comparison, to finding models that optimize the prediction of new data. So just to show you an example of generalized additive modeling in practice, This is data from a paper that's in press over at JEP Gen right now. It's from my master's thesis. In my master's thesis, I did an experiment where I collected reaction time data and error in a two alternative speeded choice task. So people had to, as quickly as they can, classify a stimulus that was flashed on the screen as one thing or another. So we had how long it took them to respond and also whether they classified things accurately or not. I had two manipulations. So the reaction data is on this row of facets, and the error data is on this row of facets. I had two experimental manipulations. The intensity of some signal that preceded the target, and there's a contingency manipulation that I won't go into, but it's think of it as a manipulation between two conditions. I also manipulated SOA, but I manipulated in a relatively continuous manner in the non-contingent conditions. So there weren't discrete bins of SOA in this condition. There were discrete bins of SOA in this condition, but relatively finely sampled. There were 16 bins across this whole range here. I certainly couldn't simply compute the bins in this condition because this condition didn't have bins. Mixed effects modeling, I also didn't want to necessarily assume that there was a linear effect of, for example, SOA on my conditions because, I didn't know that to be the case. I used generalized additive mixed effects modeling, and it yielded strong support for this model whereby there's an interaction in both of these dependent variables, such that you get these nice squiggly functions that in the paper itself we actually have description of the inferences from the draw, but you can see that there's this decrease in reaction time as a function of SOA in both of these intensity manipulations over here that's quite strong over here in this contingent condition, but there is still an effect here in the non-condition, but it's certainly not as strong over here. And there's some interesting differences amongst the actual intensity manipulations. But the idea here is that I didn't actually tell the stats to fit these functions of this specific form. It was able to just go through and find.
How do you define it?
So that's something that's a little outside the context of this particular talk. Ray is actually going to talk about it in his talk either tomorrow or Sunday. I can't remember when his talk is. But the general idea is that here SOAs are just random, whereas here people experience the same SOA for like 30 trials within a given block. So this is like a blocked versus mixed difference here. But Ray's going to talk a little bit more about sort of the design here and the applications of cognitive theory. My point here is showing that it's able to get these nice continuous, but by definition from the idea of cross-validation, predictive functions, optimally predictive functions out of the data. Another thing to note here is that even though these functions seem linear, I did apply generalized additive mixed effects modeling to these. Generalized additive models simply determined that there wasn't enough data, there wasn't enough support in the data for anything other than linear effects. So generalized additive mixed effects models reduce to linearity when the data say there's not enough data to support any squiggliness in the data. This actually kind of makes sense in the context of error data because you only get one bit of information per trial, whereas they're either accurate or not. Whereas in reaction time data, you get much more information-loaded data per trial. So this leads me, this idea of generalized additive mixed effects modeling leads me to an intriguing application that I'm currently exploring, which is resolving the problem of reaction time data. Reaction time is used very widely in cognitive science. Unfortunately, most of the stats, including mixed effects modeling as I've described thus far, assume that the reaction time distribution has a Gaussian distribution of error. However, we know explicitly that reaction time data is not Gaussian. You can just plot it up and it's not Gaussian. Indeed, people that have looked at this very carefully have found that the shape of reaction time distributions are known to be affected by different experimental manipulations. So things like Shroop, memory load, they all affect the reaction time, the shape of the reaction time distribution, not just its shift. So the idea I have is to take reaction time data, and if I say have the example of simple reaction time from multiple trials from each of many participants in each of two conditions, what I would do is for each participant in each condition, I would take the RT and label it with its percentile. So the median RT is going to be, if there's an RT at the median, it would get a 50. The maximum RT is going to get 100. The minimum RT is going to be 0. And then I'm going to add percentile as a predictor in the model. So the main effect of that predictor percentile is not going to be interesting. It's going to be monotonic. There's going to be an effect such that the larger percentile leads to a larger RT because that's how we define percentile. But what will be interesting is how that predictor interacts with other variables in our experiment. So for example, if I'm doing a two-condition experiment, how that can interact with condition. So to give you an example here, here's some actual data. Along the x-axis here is the quantile. So that means, these are the faster RTs and these are the slower RTs. And as I said, the main effect of quantile is just this monotonically increasing function. But what's interesting is comparing that monotonically increasing function between conditions. So here we've got an experiment where you've got flankers on either side of the targets, and those flankers can be either the same as the target, in which case they're called congruent, or they could be different from the target, in which case they're called incongruent. So the incongruent are these ones here, the congruent are these ones here. It's kind of hard to see by using the raw data, but these two, the mixed effects model says there's very strong support for there being an interaction between flanker congruency and the quantile function, implying that the quantile function has a different shape in these two flanker conditions, in turn implying that the reaction time distribution has a different shape in these two distributions. And to actually show that effect of flanker on the quantile function, I can collapse that previous plot of two different functions to a different score between these two functions. And what you can see here is this function such that at early RTs, there's a difference between those reaction time distributions of about 60 milliseconds. And as you get to later RTs, you get an even larger effect. So the flanker effect is larger at slower RTs, which is inferentially which is theoretically pertinent. I've also been exploring summarizing these plots, or for example, summarizing these plots in terms of metrics of the shape versus the scale or the shift of the distribution. This plot shows that the shape of the distribution, how skewed they are. So this reflects the higher value means that there's more skew. So this plot shows just from the model the idea that the congruent distribution actually has more skew than the incongruent distribution. The error bars are a little misleading insofar as this actually is a reliable difference if you do a 95% confidence interval on the difference between these two poles. So that's something I'm playing with, giving one the ability to get a little bit more nuance in the analysis of reaction time data. There have been tools for people to analyze the full distribution characteristics of reaction time data for a long while, but they've typically been rather cumbersome. You, again, for each condition and each person, have to estimate parameters of an a priori model, and then from that, you'd submit those independently to different analysis procedures, whereas this kind of does it all at once. So I'm quite interested in this. If you're interested, there's actually a recent paper it's in the latest issue of Behavior Research Method. Wolf Schwartz and Jeff Miller have a discussion of what they call delta plots. And this is very analogous to delta plots. Delta plots are basically an early version of what I'm doing here. It's non-mixed effects modeling approach, and generalized additive modeling, but it's very similar in terms of the ultimate idea of characterizing the full shape distribution and comparing conditions from that. So how are we doing for time here? 4 o'clock. Oh, okay. Wow. Okay. Hopefully, well, at the end I'll stop for questions and I can go back over things if I've gone too fast. I'd like to stop, or I'd like to end with describing how to use these tools. So I've described all these different models. These models have the ability to characterize different scenarios very efficiently and accurately, but how do we use these models to answer questions, answer our scientific questions? So, while it is possible to compute p-values, as we traditionally see in our statistical literatures, it is possible to compute p-values in a mixed effects model. It's very hard and it's very contentious. I generally just sidestep that whole area of debate because I strongly believe that it is a fact that p-values are not what we think they are. That is, if you ask people what a p-value, if you ask most researchers what a p-value is, they will tell you the wrong answer. They don't know what a p-value actually is. And when you ask them what they want in a sort of inferential metric, they describe something that's very close to what a likelihood ratio is. The likelihood ratio is the metric of evidence. And I highly suggest you look at this reference right here. It's in a relatively obscure journal, but it's a beautiful summary of a lot of arguments against, first of all, against p-values as tools for scientific inference, but also for likelihood ratios and description of likelihood ratios. It's in the Journal of Scandinavian Psychology. It's got a fun title, Hail the Impossible, and then some subtitle that I can't recall at the moment. But very good reference, very good summary, I should say. And the idea is likelihood ratio. So I'd like to actually describe to you precisely what a likelihood ratio is. Let's say that we have a bunch of height measurements for men and women. So we've got these backslashes, these purple backslashes as the heights we've determined from women, and these light blue forward slashes as the heights we've measured from men. And this is maybe our meter stick, and we've just laid it on top. So the likelihood ratio asks you to develop two models for the data and then compare them somehow. So one model that we have for the data is that all these heights just come from a single Gaussian distribution whose center is somewhere around here, and whose variability, or that has some variability associated with it. So if that's our model, what one can do is actually establish the likelihood of that model given the data. So to do that, what one would do is, for each data point, you'd ask, how high is this curve over top of that data point? So where is it on the y-axis over top of that data point? And then we do that for another data point. And once we do that for all the data points, once we get the height of the curve over all the data points, you simply take a product of all those values. So the height of the curve reflects the probability density of that point. You can think of that as the probability of that point given the model. And then the product of all those probabilities reflects the probability of all those data given the model. And the likelihood of a model given data is actually just defined as the same thing as the probability of the data given the model. There's a slight nuance, but I won't talk about that. So you can establish the probability, or the likelihood of this model, where you've got this single curve, and then you can similarly establish a second model, where you say, oh, I'm going to say that this data comes from two different curves. So one curve has its mean over here, and has this amount of variability. This other curve has its mean over here, and we'll just say that it has the same amount of variability. And here, for each point you'd have to establish the probability of each of these data points, you use this curve. For each of the blue data points, you use this other curve here. So for example, this point here, or let's use this, the purple point that's here, purple backslash, would use the height that's around here, whereas the blue forward slash would use this height right there, even though they're about the same location on the axis. But again, once you have all the heights at their respective curves, you simply take the product, and that product reflects the likelihood of the model, two distribution model, given this data. So, as I said, for each model, you'd say you compute the probability of the data given the model, which is equivalent to say, looking at the likelihood of the model given the data. You do the same thing for model 2. The probability of data given the model, equivalent to looking at the likelihood of the model given the data. And then you simply compute the ratio of these two likelihoods. So it would be the ratio of this versus this. It turns out that computers don't like simply doing this on the raw scale of the probability of the data. It's much easier to compute this whole thing if you use the log scale. So the idea is that you just log transform this axis. And it makes it so that instead of taking the product of many small numbers, many probabilities tend to be less than 1, and the probability densities tend to be less than 1. Instead of having to multiply lots of small numbers, which yield very, very, very small numbers, you're adding not small numbers. The log transform makes it so that you're just adding positive numbers, which is very easy to achieve. You'll see likelihood ratios usually on the log scale. And I like to represent them on a log base 2 scale. The idea here is that you can actually refer to the likelihood ratio as reflecting the bits of evidence. So bits truly in the sense of information theory. And so it would be the likelihood ratio would reflect the bits of evidence for or against some model relative to the other model. Now, there's a nuance here that I haven't talked about yet, which is that in the same way that I described fitting a function through that x and y data, the best fitting function, the best fitting model for that data is one that simply connects the dots. But presumably that's not going to do well at predicting new data. So in the same way, you need to account for that in the fitting of functions through data. You need to do that in establishing models of data that's maybe not sort of an explicit x versus y function. So you need to correct for the complexity of your models. More complex models will usually have better fits to data just by dint of being more complex. They have more flexibility to accommodate error in the data, which means that if they're predicting error, when you try to use them to predict new data, they're not going to do very well. So your estimation of more complex models, they'll look like they fit better, but they actually may fit worse than less complex models. And you need to somehow account for that. So again, the models that we've just discussed, we've got a single distribution with a single mean and a single variability versus this other model that had two distributions. So you had at least two means. The way I talked about it, we just kept the variability the same between the two, conventional assumption. But they definitely differ in the number of parameters. So the model 1 had 2 parameters, mean and variance. Model 2 had 3 parameters, 2 means and 1 variance. So again, as I said, model 2 may be fitting better simply because it has more flexibility to spuriously fit error. So again, we're going to use that gold standard solution, which is cross-validation. So in this context, to establish the likelihood of model 1 given this data, what we're going to do is temporarily forget a data point. So that one way on the far right. So we're going to forget that data point, establish the parameters of this model, the mean and variance, given all the other data points, and then bring that data point back in and establish its height in this new model. and then repeat it again for each data point in the thing. So for each model, in each data point, we estimate the parameters of the model from all the data accepting that data point, and we establish the likelihood of that data, or the probability of that data point under the model, given that data point and the distribution parameterized by all the data except that data point. So again, it's a nice gold standard solution. It ensures that when we are comparing models, we are comparing on the ability to predict future data, which is fundamentally what we're trying to achieve in science. And that's what that point says. So that seems like a lot of work to actually go in and estimate the parameters of the model for every single data point that you collect, particularly in cognitive science, where you may have 1,000 data points per person. So there's actually, it turns out, a nice approximation to the full process of cross-validation. It's an analytic formula that simply establishes, given this many parameters in this model, how much you should subtract out of the likelihood of the model. So models with more parameters get more strongly penalized, and it turns out that it's asymptotically equivalent to cross-validation. There's some variability in that with small sample cases, but in general, it's a good approximation. If one truly had the time, you could just do cross-validation, but most of the time, we just use the AIC as an approximation of cross-validation. So I've talked about this idea of likelihood ratios for inference. How are we going to apply it in the context of mixed effects models? Well, it's pretty simple. We'd establish two models. One model that has, say, one structure. So reaction time is a function of grand mean, plus you account for the variability amongst subjects and their deviation from the grand mean, plus trial by trial error. And then another model that has the exact same structure, but adds just one thing. Here, that thing is a overall difference between the conditions in their effect. And therefore, the likelihood ratio will reflect how much evidence there is for an overall difference between the two conditions in that effect. You can do the same thing in terms of assessing variability components and use likelihood ratio for, say, the correlation between individual difference measures. But it's relatively straightforward. So I can't remember what else I have here. Oh, so this is an example of a slightly more complicated scenario. Model 1 includes two main effects. So it's got all this stuff that we're used to, grand mean, deviations of subject from the grand mean, and error. But now we've got the main effect of that's the condition effect, and then an instruction effect. And model 2 had, again, all that stuff, but it additionally has the condition effect by instruction effect. And the comparison of these two models would permit evaluation of the evidence for an interaction between those two variables. So that's all the slide content I have. If anybody has any questions, clarifications on any of this, I am happy to answer your questions. It assumes that it assumes that the error is normally distributed, and that each of the variances that you're associating. So, for example, subjects deviation from the grand mean, that therefore subjects are normally distributed. So it does have assumption of Gaussianity when that's in effect. I've heard that said. But I've heard that said of ANOVA as well, right. And I haven't looked into the degree to which people have actually parametrically manipulated the degree of violation of assumptions and see how it affects inference. So that's not something I can speak to. Oh yeah, certainly. So I've actually been recording this the whole time, and I will also share just the raw slides as a PDF. But we've also got the video and audio. Any other questions? points of clarification where I went too fast? All right. I guess I will. Oh, go ahead.
Yeah, I've got one. One of the things that oversight
Right.
So I started wondering whether or not that same kind of question.
Oh, certainly.
One of the reasons why is that most of the work that I've done focused on
Mm-hmm.
so this, I guess I'm asking a comment on that. Just simply, because it captures variance,
Mm-hmm.
this is stronger factors.
The assumption, I guess, so Sternberg actually had the prediction that you're going to have a larger variance in one condition versus another. I'm not sure that that can come out in the mixed effects models from the perspective that it assumes that error variance is always the same across all your conditions, that you may have variability between subjects in the manifestation of an effect, but your error variance is always the same. So that is something that's, I guess, possibly is not testable unless you went to the approach that I take, which is you explicitly quantify the distribution of your, I guess, error by labeling, by labeling each, I guess, observation with regards to its percentile in the distribution that you're looking to characterize. Yeah. Yep. Yeah. Brought on the variances as well. Yeah. Yeah. No, I think certainly using sort of my I guess trick that I'm playing with of adding the percentile as a generalized additive model predictor should be helpful in that context. But it also should be helpful in the context of analyzing error data, because typically when people analyze error data, they collapse to a proportion. But I can't recall if it was Sternberg or something coming after Sternberg pointed out that proportions shouldn't be additive in the context of Sternberg's additive factors logic. They should be multiplicative or something like that. When you do it with binomial data, I have to double check the Sternberg's additive factors logic and work out maybe some simulation. Yeah, but it should reduce back to the fundamental. It should reduce back to the idea of additivity versus interactions when you treat the data as properly binomial. Yeah. It's just sort of yeah, exactly. Yeah. Any other thoughts or questions? Yeah. Okay. Yeah. Mm-hmm. Well, insofar, so you can certainly always collapse your data to some descriptor and then submit that collapsed data as in a mixed effects model. The mixed effects model doesn't necessitate that you give it the raw data. It prefers you do, and you get more powerful that you do. But if you're doing it that way, all your inferences will be at the level of the mean, unless you use my percentile approach, in which case you can actually make inference on the on the median by looking at the 50th, where that thing hits the 50th percentile. But the reason that people are doing that is because the reaction time distributions tend to be particularly skewed in very young groups and in clinical groups. If that's the case, I'd say the solution is to use tools that account for that shape, again, like percentile method, rather than try to just use some trick to try to ignore those shape differences. So that would be good on that. So there was actually a point that I didn't actually develop a slide for, so I forgot to mention it before the end of the talk. But I will say that the approach to inference that I described here is one that has discussion in the literature in general in terms of likelihood ratios. In the context of mixed effects models, not as much. Most of the folks using mixed effects models are, again, people tend to shy away from p-values because frequentist p-values, the ones that you're used to coming out of ANOVA, are hard to define just mathematically from the mixed effects modeling context. However, people do generate p-values for a lot of mixed effects modeling, but these are Bayesian p-values. So the idea here is that from the Bayesian perspective, what one does is they approach a scenario like this where you are interested in the effect of a, say, the interaction or not, and one would define a distribution of the values for the interaction coefficient that one believes a priori to be a likely distribution. And then you fit the model to the data. The model gives you a, well, there's a component called the Bayes factor that's very similar to a likelihood ratio. And that Bayes factor is used to update your prior beliefs with regards to what the new data is telling you. So that yields now a new distribution of belief, an updated distribution of belief, and you can compute p-values from this new distribution. So Bayesian analysis permits an objective way of updating subjective belief. People have described, there's, I don't think I created a reference for it, but there's a Forster and Sober 2004, I believe it's a chapter, the title of the chapter is called Why Likelihood, but I can't remember the name of the book that it's in. But they create a nice summary of the frequentist versus likelihood versus Bayesian approaches in answering different questions. The frequentist question asks is a solution to dealing with controlling a certain type of error rate of decision across a long sequence of repeated decisions. Not something that scientists usually want to care about, even though we tend to use frequentist p-values all the time. The likelihoodist approach is simply trying to say, what is the evidence for and against a given model relative to another reasonable model? And what is the objective evidence? The Bayesian says, given my prior beliefs and this new objective evidence, how should I update my beliefs? So Bayesians, the likelihoods say, what does the data say? The likelihoods, the Bayesians say, what should I believe? Ultimately, we're all Bayesians. There's plenty of research talking about how the brain has Bayesian or quasi-Bayesian processing modules, but even at a higher level, we all tend to have prior beliefs and we let data update those beliefs. So we do Bayesian stuff in our head. I'm not enamored right now of doing the Bayesian explicitly in my data analysis because that forces my subjective beliefs on other people. Bayesians have argued that you can specify relatively naive prior beliefs, and that makes it so that you should encompass many people's subjective beliefs. But frankly, I think with the current system of scientific communication, where you present one results section and that's sort of firm, that's I'd rather present the objective data from the data that I've collected, the objective evidence from the data that I've collected, and let people sort of do that Bayesian inference in their head. In the future, maybe we'll have scientific communication such that you have an online dynamic interface to the data. You can pre-specify your own priors and let it do all the Bayesian computation to yield out what's the data say with regards to your priors, but we're certainly not there yet. Logically, we actually probably are, but in terms of infrastructure, we're not. So until that point, I prefer to go with the simply present the objective evidence, let people do the Bayesian computations informally themselves. But I will say that the Bayesian approach is, you will see that more frequently when you see the mixed effects modeling. The likelihood approach is something that's really it's a much smaller group of people doing it, i.e. so far through my knowledge. But I have provided nice, simple tools for people to apply these mixed effects models. I haven't talked about how to actually compute things. That's because I've mostly developed tools that do this automatically for you. It's in the software package called R, and it's specifically an add-on package called Easy. So if you're interested in that stuff, email me. I'll send you the link to a site that describes how to actually install the very, very cutting-edge version of Easy that has very cool stuff like the percentile.
And all of
Pardon me? Eventually. Yeah. The documentation I still have to update to include all the tweaks and new stuff that I've actually included over the last few months. But, that's a little bit of work in progress there. Oh yeah, certainly. Yeah. No, as I said, I'm quite evangelistic with regards to mixed effects models and the power and simplicity that they provide. So I'm certainly willing to field questions and help out. All right. Well, thanks everybody for your attention, and have fun at the symposium.